Alright, so with this information that I have over here, let us see if we can go forward and compute all the DF values. Okay. So, in order to talk about the DF values, we need to sort of understand what are the different edges that are present in this data flow graph to start with, right. What I mean by that is, even though because what I have drawn over here is not really a data flow graph, it is a block diagram, right. So, there are, for example, these junction points over here where something splits off into two, or when multiple mergers of course are indicated by additions, but the splitting off of into two, right, as far as the block diagram is concerned is a clean way of drawing it, but as far as the data flow graph is concerned, that is actually hiding some information, because these points that I have over here, those junction points, are not really separate nodes in the data flow graph. So, if I look at what are all the edges that are present in the DFG, I find, for example, that I have an edge from which is going from A1 to M2, right. Another edge is going from A1 to A2, and the edge from A1 to A2 has one delay element on it. The edge from A1 to M2 also has one delay element on it. The edge from A1 to M4 has two delay elements on it, because when I take that path I have to pass through two such registers, two delay elements. Okay. So, there are two options available to you here. Either you just go through this and make sure that you count the number of delay elements properly, or you redraw the original block diagram as a data flow graph just for clarity, so that the exact number of delay elements are easily visible. So, obviously there are more edges, right. I am not going to draw every single one of them over here, you can do that quite easily on your own. So, what I am going to do instead is try and calculate the DF values, right. So, let us look at, for example, the DF value between edge A1 to A2, right. How would I compute it? I need the schedule time of A2, which in this case is 0, minus the finishing time of A1. A1 is an adder, it is scheduled at time 2, it has a pipeline latency of 1, okay. So, this is what I have, this is T of A2 minus finishing time of A1. So far it does not look good, it is looking negative, but I have one delay element. So, plus 1 into 4. So, DF over here becomes equal to 1. Okay. Let us look at DF from A1 to M2. In this case, once again, the schedule time of M2 is 2. The finishing time of A1 is 2 plus 1 equal to 3, okay. Again it would have been negative except for the fact that there is one delay over here. So, what I get is 4 plus 2, 6 minus 3 is equal to 3, right. What about the DF from A1 to M4? In this case it is 1 minus 3 plus 2 into 4, okay. So, 1 minus 3 minus 2 plus 8 is equal to 6, right. Similarly, I can go ahead and calculate all the M values. One particular example I am just going to take because it also brings out, for example, the fact that we are using a multiplier is from M2 to A4, okay. So, the DF that I would have from M2 to A4 would be equal to, what time is A4 scheduled? It is at 3. What time does M2 complete? It is scheduled at 2 and it has a pipeline latency of 2, okay. So, 3 minus 4 plus 1 into 4, right. So basically it becomes 4 minus 1 is equal to 3, right. And in this way, one thing that you can see over here is, for example, just to sort of simplify this, or rather one example over here is where W is equal to 0, right. So the A3 to A1 edge, df from A3 to A1, when is A1 scheduled? A1 is scheduled at time 2 minus A3 is scheduled at time 1, and it has a pipeline latency of 1 because it is an adder, plus 0 into 4. This is an example where it is 0. Okay. So in other words, all that we really need to do is work through every single edge in this graph and make sure that the resulting df values are non-negative. They can be 0 or some positive value. Okay. As long as they are 0 or some positive value, it means that this set of schedule instants that I chose, right, or the folding sets that I chose are valid. There is no violation over here. What does the hardware architecture corresponding to this look like? It would be, I have one adder and one multiplier. Like I said, I am basically drawing two registers after the multiplier to indicate that it is pipelined to a depth of 2. I do not really need to do that. How it is implemented internally, I do not really care. Now the thing over here is, there are 4 different options, right. Right, and once I have this architecture in place, all that I need to do is find out at phase 0 what is supposed to be computed on the adder. Let us go look at our schedule. At phase 0, A2 is going to be computed on the adder. Okay. Where are the inputs to A2 coming from? They are both coming from the adder itself, okay, because the inputs to A2 are, one is from A1 and the other is from A4, right. In other words, both are some outputs that were generated by the adder at some previous instance of time. Okay. So just for understanding, let us put down this over here. This is corresponds to W equal to 0, and the df value on A4 to A2 is, in this case, 0 minus, sorry, I think I have got these numbers a little bit wrong. This should actually have been, so in other words, actually this is a problem, right. As you can see over here, if I actually had these values, it means that there is a problem over here, right. So what I have is 0 minus 3 plus 1. This is definitely not acceptable. So it turns out that the numbers I had put down over here, I think I had actually made an error over here inadvertently. Okay, I will correct it and I will put the updated thing. We will go over that once again briefly in the next class if necessary, but let me just correct it for now. This should actually be, this should be 0, this should be 1, 3 and 2. Okay. It does not really change any of the other computations too much, so do not worry about it. You can actually just go through and calculate and verify the rest of the values. Some of these df numbers of course will change. You need to recompute them because the A1, A2, all of these values have now changed, right. The m values do not change, but the a values, because I have updated them, you will need to recompute them. Okay. So once I have this updated value anyway, what would happen is, with this what I would get on df from A4 to A2 would be 1 minus 0 plus 1 plus 0. So df would be equal to 0. Okay. And the df over here would be from A1 to A2 would be equal to 1 minus 3 plus 1 plus 1 into 4, or in other words is equal to 1. Okay. For now, these are the only two numbers that I care about, so that I can at least tell you what happens at, well, time instant 1. Okay, I need to correct this, right. If I have this structure, then essentially what I am going to say is, going down to my next diagram, at time instant 1, what are the two inputs that I should have coming into my adder, right. I am going to say that the top one corresponds to the output from A1 and the bottom one corresponds to A4. I am just arbitrarily making that choice. Where does that actually physically come from? The output A1 to A2 is the output of the adder, but with one extra delay on it, whereas A4 is the output of the same adder, but with df equal to 0. So now you can see how you would go about constructing the entire structure, right. What I am going to do is, I will stop over here because we have run out of time for today's class. You can of course go ahead and just complete this. In addition to that, we have some questions in the tutorial that also deal a little bit further with some examples of this sort. It is well worth doing that. The thing that you need to keep in mind is simply this: what is it that you are finally trying to do? You have come up with a proposed architecture which has one adder, one multiplier in this case. You have found out the scheduling time instants, the folding sets, they have been given to you right now, right. You do not know how to find them, but they have been given to you. Once they are given to you, you can then go ahead and calculate all the df values, and once you have the df values, you can then just basically say, okay, at time instant 1, the adder was supposed to execute this particular operation A2. Where did it get its inputs from? From A1 and A4. A1 and A4 are both outputs of the adder. What are the df values for that? For A1 it is 1, therefore put one register and take the output. For A4 it is 0, so directly take the output of this pipelined adder and feed it back to time instant 1.